All right, welcome to this explainer. Today, we're getting into the absolute bedrock of cybersecurity. We often picture cyber defense as this incredibly high-tech world full of flashing screens and complex algorithms. But honestly, the reality is a whole lot more grounded. To actually understand how to defend a system, or how an attacker exploits one for that matter, you first have to understand the physical and logical roads and highways that data travels on, because you can't spot anomalies if you don't even know what normal looks like, right? So let's jump right into this quote from the source material, because it really hits the nail on the head. In cybersecurity, networking is the ground beneath your feet. It's just a perfect way to frame it. Literally every malware payload sent across the web, every firewall rule a security analyst configures, every packet inspected in a SOC, and every single exploit fired off in a penetration test relies entirely on this very ground. Basically, without networking, there is no cybersecurity. Period.
So to get us fully comfortable on that ground, we're going to break this massive topic down into 5 manageable pieces today. First, the networking foundation. Second, addresses of the internet. Third, opening the right doors. Fourth, the core protocols. And finally, number 5, your hacker toolkit. Let's dive in.
Starting off with Part 1, the networking foundation.
Okay, when we look at the big picture blueprint of how data actually moves between systems, theorists and textbooks really love to focus on the 7-layer OSI model. But out here in the real world, the living internet actually runs on this highly practical 4-layer TCP/IP stack. Data travels down this stack on the sending device, a process we call encapsulation. And then it travels right back up the stack on the receiving device, which is decapsulation. It flows from the application layer at the very top, down through the transport layer for end-to-end communication, through the internet layer for logical routing, and finally hits network access at the bottom for physical transmission over Ethernet or Wi-Fi. And grasping this flow is absolutely crucial, because attackers specifically target different layers. Web exploits like SQL injection, those hit the application layer. Meanwhile, a denial of service attack, or a DOS flood, typically targets the transport or internet layers to just totally exhaust a server's resources. You've got to know exactly which layer you're actually defending.
Moving right along to Part 2, addresses of the internet.
Now that we've got the blueprint, let's zoom in on that internet layer, where every single device needs a literal street address to be found. Now for decades, that address was IPv4. This is that classic 32-bit format of 4 numbers separated by dots, like 192.168.1.1. But here's the problem. It has a hard cap of about 4.3 billion addresses. And with smartphones, laptops, and now smart fridges all coming online, we just completely ran out of room. So we had to evolve. Enter IPv6. These are massive 128-bit hexadecimal strings designed to make sure we never, ever run out of addresses again, even with billions of new smart devices constantly connecting to the web. But hey, regardless of whether you're using version 4 or version 6, there is a very strict dividing line you have to understand, and that is the difference between public IPs and private IPs. Public IPs are globally unique. They're assigned by your internet service provider, and they face the dangerous wide-open web. Private IPs, on the other hand, are strictly for local networks, like the one inside your home or your office. Ranges like 10.0.0 or 192.168.0.0 are completely non-routable on the public internet. They're safely tucked away.
But wait a second, if private IPs can't route on the public internet, how is your phone connecting to the web from your home Wi-Fi right now? Well, the answer is NAT, or Network Address Translation. And NAT is an absolute game changer. It basically takes all the private local IP addresses inside your house and translates them into just one single public IP address when they need to talk to the outside world. Not only does this let hundreds of devices share one public IP, saving us tons of precious address space, but it also gives us a massive security benefit. It completely hides your internal network topology from external attackers. All right, on to Part 3, opening the right doors.
Think about it this way. If an IP address gets your data to the right apartment building, how does it know which specific apartment door to knock on? The answer is ports. And there are exactly 65,535 possible ports on a single operating system. It's a huge number, and it allows an OS to run dozens of network services simultaneously, without, say, your web traffic getting totally mixed up with your email traffic. The ports from 0 to 1023 are what we call well-known ports, reserved for core system protocols. Then, from 1024 up to 49,151, you have registered ports for specific user applications. And the remaining numbers, all the way up to 65,535, those are dynamic or private ports, used temporarily just for client connections. Now, to actually send data to those 65,000 different doors, applications have to pick a delivery method at the transport layer. They basically choose between TCP and UDP. TCP, or Transmission Control Protocol, is your careful delivery driver. It's connection-oriented. It requires a highly reliable three-way handshake, SYN, SYN-ACK, ACK, to practically guarantee that your packets arrive intact and in the right order. It's absolutely perfect for web browsing and file transfers. But UDP, User Datagram Protocol, that's like a rapid-fire t-shirt cannon. It's totally connectionless. Fire and forget. It prioritizes blazing speed over reliability, making it the absolute go-to for things like video streaming, online gaming, and DNS queries, where a single dropped packet really isn't the end of the world.
Which brings us to part 4, the core protocols. Heading back up to the application layer for a minute, we can see how the guards at those port doors actually talk to each other. Take DNS, the domain name system, which hangs out on port 53. It's universally known as the phone book of the internet. See, when you type a human-readable domain name into your browser, your computer actually has no idea what that is. It needs the IP address. So it kicks off this sequential resolution process. Your query hits a recursive resolver, which then checks the root servers, bounces to the top-level domain servers, and finally reaches an authoritative name server. Step by step, it translates that human-readable domain into the computer-readable IPs we talked about earlier.
Next up, we have the protocols that actually fetch your web pages, HTTP and HTTPS. HTTP operates on port 80, but here's the catch. It transmits data in completely vulnerable plain text. Literally, if you're logging into a bank over HTTP on public Wi-Fi, anyone sniffing that network can read your credentials, your cookies, and your session data right there in clear text. No way around it. And that is exactly why HTTPS on port 443 is mandatory today. The S stands for secure because it secures that HTTP traffic using Transport Layer Security, or TLS. It encrypts everything between your browser and the web server, protecting both your data's integrity and its confidentiality.
Beyond just web browsing, system administrators need a way to remotely manage operating systems, especially Linux servers. For that, they use SSH, or Secure Shell, on port 22. This completely replaced legacy, unencrypted tools like Telnet on port 23. And what makes SSH so incredibly powerful is that it uses cryptographic key pairs, a public and a private key, for highly secure access. It effectively locks out unauthorized users who might just be sitting there trying to guess a simple password over an unsecured network.
Now, we just talked about how these protocols work normally, but in the real world, these everyday functions are constantly weaponized. Attackers will use DNS cache poisoning to inject fake IP addresses and route users to malicious sites. Or they'll use DNS tunneling to sneak malware, command and control traffic right past your firewalls. For HTTP, they aggressively sniff plain text sessions. And for SSH, any service left exposed to the public internet is facing relentless, around-the-clock, automated brute force attacks, just constantly trying to guess weak passwords.
All right, final section. Part 5, your hacker toolkit. The battlefield is set, but to actually defend this architecture, you need to be able to see it. So here's a practical toolkit you can start playing with today to really solidify these concepts. You've got ping to check basic reachability using ICMP packets. You've got NSLOOKUP or dig to manually query DNS servers and see exactly what IP a domain resolves to. Traceroute is awesome. It lets you map every single router hop your data passes through to reach its destination. To see those 65,000 doors we talked about, just use netstat or SS to list all the active open listening ports right on your machine. And finally, the big one, Wireshark. This is a free packet sniffer and network analyzer. Boot it up and you can literally watch the invisible data flow of web page loads or pings happening in real time. It's pretty amazing.
So we've covered the core framework, the addressing, the ports, the protocols, and the tools. But before you close this explainer and run off to dive into advanced penetration testing, I want to leave you with one foundational question to test your new mastery. What happens step by step during a TCP three-way handshake? Think about it. Every single time you open your laptop or check your phone, thousands of these TCP handshakes and UDP streams are happening entirely invisibly in the background, pinging servers all over the globe. If networking really is the ground beneath your feet, just how secure is the ground you're standing on right now? Keep exploring, and I'll see you in the next one.